Welcome to the lecture on complex analysis, probability and statistical methods. In my previous lecture, I discussed about what is population, what is sampling, and also about the types of samplings and the sampling distribution, and also about the null hypothesis and alternative hypothesis. In this lecture, I am going to discuss few more concepts on sampling distribution. The first concept is here errors. So while testing a hypothesis, we usually come across two types of errors. They are called type 1 error and type 2 error. So first we will see what is meant by type 1 error. If a null hypothesis is not accepted while it should have been accepted, such an error of not accepting the true hypothesis will be called as a type 1 error. So if true hypothesis is there but it is not accepted, so those kind of true hypothesis, cancelling the true hypothesis will be called as an type 1 error, and it is denoted by the symbol alpha. The probability of correct decision in case of type 1 error is given by alpha minus 1. So next is type 2 error. If a null hypothesis is accepted while it should have been not be accepted, such an error of accepting the false hypothesis will be called as a type 2 error. So if some false hypothesis will be there but it hasn't accepted, so those kind of error will be called as a type 2 error, and it is denoted by beta. The probability of correct decision in this case is given by 1 minus beta. So this is the table called how to check the type 1 and type 2 error. I am taking hypothesis is true here, hypothesis is false. Here I am taking accept h0 and non accepting the h0 value. Suppose if hypothesis is true and if I accept the hypothesis h0, so it leads to correct decision. Suppose if hypothesis is true but I am not accepting the hypothesis here, so it leads to type 1 error. Again, hypothesis is false but I accepted the hypothesis h0, it leads to type 2 error. Suppose the hypothesis is false, if I not accept the hypothesis, so it will be obviously correct only, so it will be called as a correct decision. So next, significance level. The probability level below which leads to the non-acceptance of the hypothesis will be called as a significant level. So this probability is conventionally fixed at 0.05 and 0.01, or we can denote like 5% or 1% called as a significance level. Actually we feel confidence in non-accepting the hypothesis at 1% level than the 5% significance level. So the 5% level of significance can be understood as the probability of committing errors of their types. I mean type 1 and type 2 error will be given by 0.05 here. So next, so now we'll see how to test the significance and also about the confidence interval. The process which helps us to decide about the acceptance and non-acceptance the hypothesis will be called as a test of significance. Suppose we have a normal population with mean mu and the standard deviation sigma. Suppose if x bar is the sample mean of random samples of size n and the quantity z is defined by z is equal to x bar minus mu by sigma into square root of n. So this is called as a formula for the standard normal variate. So from the table of normal areas, we found that 95% of the area lies between z is equal to minus 1.96 and z is equal to plus 1.96. In other words, we can say that with a 95% confidence that z lies between minus 1.96 and plus 1.96. Further, 5% level of significance is denoted by z 0.05. Now also similarly from the table of normal area, the 99% area lies between minus 2.58 and plus 2.58. That is 99% confidence that z lies between minus 2.58 and plus 2.58. 2.58. So further, the 1% level of significance is denoted by Z 0.01. So this is a formula of to find the significance level that is given by x bar minus 1.96 into sigma by square root of n less than or equal to mu less than or equal to x bar plus 1.96 into sigma by square root of n. And so this is for 5% level of significance, and it is given by x bar minus 2.58 sigma by square root of n less than or equal to mu less than or equal to x bar plus 2.58 sigma by square root of n. This is for 1% significance level. So hence we can say that the equation 1 is the 95% confidence interval, and the equation 2 will be the 99% confidence interval. So this is called normal curves to denote that that 95% significance level and the 99% significance level. So next is one-tailed and two-tailed test. So in our test, the acceptance or the non-acceptance of the hypothesis, we concentrate on the value of z on both sides of the mean. So this can be categorically stated that the focus of attention lies in two tails of the distribution. So hence such a test we will call as an two-tailed test. Sometimes we will be concentrating only on the extreme values to only one side of the mean. So in such cases, the region of significance will be the region of one side of the distribution. So obviously the area of such region will be equal to the level of significance itself. So such a test will be called as an two-tailed test. So it means that if you are concentrating on both sides of the mean will be called as a two-tailed test, and also if you concentrate only on one side of the distribution will be called as a one-tailed test. So the critical values of z in case of one-tailed and two-tailed test is given by, for the one-tailed test the 5% level of significance is given by minus 1.645 or plus 1.645. The 1% significance level is given by minus 2.33 or 2.33. In case of two-tailed test, the 5% level of significance is given by minus 1.96 and plus 1.96. And in the case of 1% level, we'll be having minus 2.58 and plus 2.58. So now test of significance for large sample. So if the sample size is greater than 30, we have to use the concept of test of significance of large samples. So here the first concept is test of significance of single proportions. So this test is used to find the significant difference between the proportion of the sample and the population. So let x be the observed number of success in sample size of n, and the expected number of success will be given by the formula z is equal to x minus mu by sigma. Or also we can use this formula like z is equal to x minus np by square root of npq. Since mu is given by np and sigma is given by npq, I can use this formula here. So next is confidence interval. So if z is greater than 2.8, we conclude that the difference is highly significant and the hypothesis will not be accepted here. Since p is the probability of success and square root of pq by n is a standard error, therefore p plus or minus 2.58 into square root of pq by n will be the formula to estimate the probable limits in case of the single proportions. So in the next lecture, I'm going to discuss about the problems related to the sampling distribution. Thank you.